Hello and assalamu alaikum. I am Dr. Yo and welcome back to my thermodynamic class. Today we will learn chapter 3, that is energy analysis of closed systems. We go to the overview and objectives. In chapter 1, we considered various forms of energy and energy transfer, and we developed a general relation for the conservation of energy principle or energy balance. Then in chapter 2, we learned how to determine the thermodynamics properties of substances. In this chapter, we apply the energy balance relation to systems that do not involve any mass flow across their boundaries, which is closed systems. We start this chapter with a discussion of the moving boundary work or PDV work commonly encountered in reciprocating devices such as automotive engines and compressors. We also identify the first law of thermodynamics as simply a statement of the conservation of energy principle for closed, fixed mass systems. We continue by applying the general energy balance relation, which is simply expressed as E in minus E out equal to delta E system, to systems that involve pure substance. Then, we define specific heats, obtain relations for the internal energy and enthalpy of ideal gases in terms of specific heats and temperature changes, and perform energy balances on various systems that involve ideal gases. Moving boundary work. One form of mechanical work often encountered in practice is associated with the expansion or compression of a gas in a piston cylinder device. During this process, part of the boundary, the interface of the piston, moves back and forth. Therefore, the expansion and compression work is often called moving boundary work, or simply boundary work, figure 3.1. Some call it the PDV work for reasons explained later. Moving boundary work is the primary form of work involved in automobile engines. During their expansion, the combustion gases force the piston to move, which in turn forces the crankshaft to rotate. The moving boundary work associated with real engines or compressors cannot be determined exactly from a thermodynamic analysis alone because the piston usually moves at very high speeds, making it difficult for the gas inside to maintain equilibrium. Then the states through which the system passes during the process cannot be specified, and no process path can be drawn. Work, being a path function, cannot be determined analytically without a knowledge of the path. Therefore, the boundary work in real engines or compressors is determined by direct measurements. In this section, we analyze the moving boundary work for a quasi-equilibrium process, a process during which the system remains nearly in equilibrium at all times. A quasi-equilibrium process, also called a quasi-static process, is closely approximated by real engines, especially when the piston moves at low velocities. Under identical conditions, the work output of the engines is found to be a maximum, and the work input to the compressors to be a minimum, when quasi-equilibrium processes are used in place of non-quasi-equilibrium processes. In the following example, the work associated with a moving boundary is evaluated for a quasi-equilibrium process. Consider the gas enclosed in the piston cylinder device shown in figure 3.2. The initial pressure of the gas is P, the total volume is V, and the cross-sectional area of the piston is A. If the piston is allowed to move a distance ds in a quasi-equilibrium manner, the differential work done during this process is Greek letter delta WB equal FDS equals PADS equals PDV. That is, the boundary work in the differential form is equal to the product of the absolute pressure P and the differential change in the volume dV of the system. This expression also explains why the moving boundary work is sometimes called the PDV work. Note in equation 3.1 that P is the absolute pressure, which is always positive. However, the volume change dV is positive during an expansion process, which is volume increasing, and negative during a compression process, which is volume decreasing. Thus, the boundary work is positive during an expansion process and negative during a compression process. Therefore, equation 3.1 can be viewed as an expression for boundary work output, that is WB, out. A negative result indicates boundary work input, which is compression. The total boundary work done during the entire process as the piston moves is obtained by adding all the differential works from the initial state to the final state. WB equals 21 PDV. This integral can be evaluated only if we know the functional relationship between P and V during the process. That is, P equal F, V, should be available. Note that P equal F, V, is simply the equation of the process path on a PV diagram. The quasi-equilibrium expansion process described is shown on a PV diagram in figure 3.3. On this diagram, The differential area dA is equal to PdV, which is the differential work. The total area A under the process curve 1 to 2 is obtained by adding these differential areas. Area equals A equals integral 2 1 dA equals integral 2 1 PdV. A comparison of this equation with equation 3.2 reveals that the area under the process curve on a PV diagram is equal, in magnitude, to the work done during a quasi-equilibrium expansion or compression process of a closed system. On the PV diagram, it represents the boundary work done per unit mass. A gas can follow several different paths as it expands from state 1 to state 2. In general, each path will have a different area underneath it, and since this area represents the magnitude of the work done will be different for each process, in figure 3.4. This is expected, since work is a path function. For example, it depends on the path followed as well as the end states. If work were not a path function, no cyclic devices, such as car engines, power plants, could operate as work-producing devices. The work produced by these devices during one part of the cycle would have to be consumed during another part, and there would be no net work output. The cycle shown in figure 3.5 produces a net work output because the work done by the system during the expansion process, the area under path A, is greater than the work done on the system during the compression part of the cycle, the area under path B, and the difference between these two is the net work done during the cycle, that is in the colored area. If the relationship between P and V during an expansion or a compression process is given in terms of experimental data instead of in a functional form, obviously we cannot perform the integration analytically. We can, however, plot a PV diagram of the process using these data points and calculate the area underneath graphically to determine the work done. Strictly speaking, the pressure P in equation 3.2 is the pressure at the inner surface of the piston. It becomes equal to the pressure of the gas in the cylinder only if the process is quasi-equilibrium and thus the entire gas in the cylinder is at the same pressure at any given time. Equation 3.2 can also be used for non-quasi-equilibrium processes provided that the pressure at the interface of the piston is used for P. Besides, we cannot speak of the pressure of a system during a non-quasi-equilibrium process since properties are defined for equilibrium states only. Therefore, we can generalize the boundary work relation by expressing it as WB equals integral 2 1 pi dV, where pi is the pressure at the interface of the piston. Note that work is a mechanism for energy interaction between a system and its surroundings, and WB represents the amount of energy transferred from the system during an expansion process, or to the system during a compression process. Therefore, it has to appear somewhere else, and we must be able to count for it since energy is conserved. In a car engine, for example, the boundary work done by the expanding hot gases is used to overcome friction between the piston and the cylinder, to push atmospheric air out of the way, and to rotate the crankshaft. Therefore, WB equals W friction plus W ATM plus W crank equals integral 2 1 open bracket F friction plus P ATM plus F crank close bracket dx. Of course, the work used to overcome friction appears as frictional heat, and the energy transmitted through the crankshaft is transmitted to other components, such as the wheels, to perform certain functions. But note that the energy transferred by the system as work must equal the energy received by the crankshaft, the atmosphere, and the energy used to overcome friction. The use of the boundary work relation is not limited to the quasi-equilibrium processes of gases only. It can also be used for solids and liquids. During actual expansion and compression processes of gases, pressure and volume are often related by PVN equals C, where N and C are constants. A process of this kind is called a polytropic process, and shown in figure 3.6. Next, we develop a general expression for the work done during a polytropic process. The pressure for a polytropic process can be expressed as equation 3.6. Substituting this relation into equation 3.2, we obtain as equation 3.7. Since C equals P1 V1 N equals P2 V2 N. For an ideal gas, which is PV equal MRT, this equation can also be written as equation 3.8. For the special case of N equals 1, the boundary work becomes as equation 3.9. For constant pressure process, the boundary work becomes as equation 3.10. For an ideal gas, this result is equivalent to the isothermal process. Energy balance for any system undergoing any kind of process was expressed as equation 3.11, or, in the rate form, as equation 3.12. For constant rates, The total quantities during a time interval Greek letter delta t are related to the quantities per unit time as equation 3.13. The energy balance can be expressed on a per unit mass basis as equation 3.14, which is obtained by dividing all of the quantities in equation 3.11 by the mass m of the system. Energy balance can also be expressed in the differential form as equation 3.15. For a closed system undergoing a cycle, the initial and final states are identical, and thus S system equals E2 minus C1 equals 0. Then, the energy balance for a cycle simplifies to E in minus E out equals 0 or E in equals E out. Noting that a closed system does not involve any mass flow across its boundaries, the energy balance for a cycle can be expressed in terms of heat and work interactions equation 3.16. That is, the net work output during a cycle is equal to net heat input, see figure 3.7. The energy balance, or the first law, relations already given are intuitive in nature and are easy to use when the magnitudes and directions of heat and work transfers are known. However, when performing a general analytical study or solving a problem that involves an unknown heat or work interaction, we need to assume a direction for the heat or work interactions. In such cases, it is common practice to use the classical thermodynamics sign convention and to assume heat to be transferred into the system, heat input, in the amount of Q and work to be done by the system, work output, in the amount of W, and then to solve the problem. The energy balance relation in that case for a closed system becomes as equation 3.17, where Q equal to Q net and equal to Q in minus Q out is the net head input, and W equal to W net and equal to W in minus W out is the net work input. Obtaining a negative quantity for Q or W simply means that the assumed direction for the quantity is wrong and should be reversed. Various forms of this traditional first law relation for closed systems are given in figure 3.8. The first law cannot be proven mathematically, but no process in nature is known to have violated the first law, and this should be taken as sufficient proof. Note that if it were possible to prove the first law on the basis of other physical principles, the first law then would be a consequence of those principles instead of being a fundamental physical law itself. As energy quantities, heat and work are not that different, and you probably wonder why we keep distinguishing them. After all, the change in the energy content of a system is equal to the amount of energy that crosses the system boundaries, and it makes no difference whether the energy crosses the boundary as heat or work. It seems as if the first law relations would be much simpler if we had just one quantity that we could call energy interaction to represent both heat and work. Well, from the first law point of view, heat and work are not different at all. From the second law point of view, however, heat and work are very different, as is discussed in later chapters.